Hello everyone, and welcome back to the Kohi game engine series. Today we are going to at least start to tackle the concept of images and textures in Vulkan. I would like to take a quick second and thank the supporters of the channel, beginning with our partners, Eearslya, Wensheng, and Caden. They are the partners of the channel, which is the highest tier of support for the channel, so thank you very much for that. And I would also like to thank all the other supporters listed here on the screen. Your support is very much appreciated, so thank you for that. Okay, so the reason I say that we're going to start to tackle this is because there is actually a lot to cover here, and it's going to be entirely too long to cover in a single video. So we're going to take a multi-phased approach to this and tackle sort of one bit at a time and get as far as we can in this video, and then we'll hopefully finish it up in the next video. So let's begin with some high-level concepts, because there are a lot of different concepts and considerations and terminology to sort of be thrown at you at once, which is one of the reasons I'm breaking this up. So first off, what do we mean when we say image? Because this can have a bunch of different meanings depending on context. And the general concept of an image is a block of memory containing color data for a given number of pixels, right? This is usually defined by some resolution, say 512 pixels wide by 512 pixels high, and a bit depth, say 24 or 32 bits per pixel. So each pixel is broken into a number of channels, for example RGBA, or red, green, blue, alpha, and a number of bits to represent that channel. Typically 8 is common. That gives a value of 0 to 255 for the red, green, blue, and alpha respectively. So those 4 channels are then combined to get the final image that you see output on the screen. As you can imagine, if you have 256 potential choices per individual channel, and then those are all combined, there are literally millions of combinations of colors that you can make with that, right? So that's why 24 or 32 bits per pixel is pretty common. The only difference between 24 and 32 typically is the inclusion or absence of an alpha channel, right? So red, blue, and green are almost always included, although there are formats that only include one of those. But typically you have RGB, or red, green, blue, and then sometimes you'll have an alpha channel, which makes up that 4th channel and the 8 additional bits. Okay? Alright, so image formats declare how this data is actually laid out, because there are a lot of different formats available and different layouts available for use. So you can have RGB, or you can have RGBA if you include an alpha, but there are also other formats like BGRA, where it's blue, green, red, alpha, or ARGB, where the alpha channel comes first. The image formats also declare things like different compression algorithms, etc. So these are all things that we're going to be covering as we continue, but I want to just keep this sort of high level for now, conceptual, right? Now, most often, these images are stored in some sort of file format. You might be familiar with bitmap or JPEG, GIF, PNG, TIFF, etc., right? There are all kinds of image formats available out there. Each has their own individual pro and con. And so at some point we will be going over some of those things. Not necessarily in detail, but sort of touching on those things, right? So those are all things to keep in mind when we talk about image generically speaking, okay? So what do we mean by the term texture? Because we said we're going to talk about images and we're going to talk about textures, and they're not the same thing. A texture is an image that is applied to the surface of geometry to provide more detail or other data to enhance the appearance of that geometry, right? This is also known as texture maps. And textures are used for many other things as well, but for now, it might help to just think of it that way, just to keep things simple, right? There are different types of texture maps, and we'll get into that as we build things up, right? So a texture is mapped to geometry using something called texture coordinates. And texture coordinates are typically in a range from 0 to 1 from the left and right, from the left side of the image to the right side of the image, and from the top to the bottom. And so, for example, in a 512 by 512 image, the pixel at 256, 256, or the center, would have coordinates of 0.5, 0.5. So to illustrate this a little bit more clearly, I actually have just a sample texture here. So let's say, for example, that we have a triangle that looks, let me actually change this color so you guys can see that. That looks something like this, right? It's pretty basic triangle, okay? And let's say that we've applied this particular texture to the triangle. How do we actually know where this texture lies, right? And so if we examine the vertices, or these individual points here, we can kind of take a look at them and guess how this might be mapped, right? So typically coordinates are mapped on the x-axis first and then the y-axis. So the x-axis here would be 0.5, and 0 would be the coordinate for this. And then we would pass along a coordinate of 1, 1 for this because it's in the lower right-hand corner. And then we'd pass along a coordinate of 0, 1 for this last vertex over here. And using these in combination with the texture itself, we can actually determine how that is supposed to be applied to that particular geometry. And as you can imagine, when you extrapolate that out over a huge mesh, you have lots of different coordinates per vertex, and that is how that mapping is applied. Okay, so that covers the concept of textures, at least in a generic sense, right? And so now we have to move on to the slightly confusing bit of Vulkan's implementation of textures. Vulkan's implementation of textures is confusingly called images, which I suppose is somewhat accurate, but it can be a little bit confusing, right? Because in Vulkan, images can be used as textures, they can be used as a lot of different things. And so you can think of, at least initially, a image as being sort of the equivalent of a OpenGL texture, but it's sort of inclusive of that, right? It's not the only thing that it is. So as you may recall, images in Vulkan are typically accessed via views. But when we want to access that in a shader, say our fragment shader, to actually apply the texture to a fragment, right? When we want to find out what that final color should be, we need one more thing called a sampler. And samplers are how shaders typically access texture data, okay? And samplers apply various types of filtering and transformations to compute the final color that is needed for a given fragment. So when we talk about filtering, this is basically what I mean. So we have basically a no filtering, or otherwise known as a nearest neighbor. So without filtering, you typically would use the texture sort of as is. And on a low resolution texture, it might look blocky, something like this, right? And anytime you have less texture resolution than you actually have fragments on the screen, in other words, how much screen real estate that occupies, you're going to get something that looks a little bit like this. And this is very, very common, right? You generally do not have textures that have a 1-to-1 or greater ratio of texels to fragments, right? And so one way to handle this is different levels of filtering, or different types of filtering. So you could apply bilinear filtering, for example, to get a sort of smooth result where it interpolates between the pixels, right? And there's various filtering methods available. There's bilinear, trilinear, and other filtering methods available. And we'll sort of touch on those a little bit as time continues, right? So that is one thing that samplers provide. The other thing that they provide is a transform. And the transform basically indicates what happens when we reach the edge of a texture. And there are several different types of this, right? And I don't recall where I got this image. I just pulled it somewhere off the internet. But basically, these are the main types of texture transformations. So the most common is repeat, where you just tile the texture, right? So when you reach the side of the texture, you just sort of repeat that texture. You also have something called mirrored repeat, which basically when you reach the edge of the texture, it starts repeating the texture backwards from that edge the other way. So you can sort of achieve a tiling effect this way without having these seams. And then you also have something called clamp to edge, which basically repeats the last pixel's color off into space. So if you exceed that 1.0 threshold, you basically just repeat the last pixels, which is what's happening here, and you sort of get this streaky kind of look. And there are instances where you'll want each one of these, so we'll touch on that when we get to it. The last one is clamp to border, which essentially just clips it and does not repeat any sort of information. In this case, it's black. So these are the various different types of transforms that are available. And that is pretty much everything having to do with texturing, at least for now. So I realize that's a lot of terminology to be thrown at you at once. There's not really too much of a way around that, unfortunately. It just is what it is. So we are going to implement a couple parts of this today. And the first thing that we're going to do is actually go into our Vulkan image class, and we're going to add a couple methods that we need, because there are some things that we actually have to do to load images in order to actually be able to use them. So right here below the Vulkan image view create, I'm going to insert two methods. And the one of these is called Vulkan image transition layout, and the other one is Vulkan image copy from buffer. So it may be somewhat obvious as to what these do, but basically this copy image from buffer takes the data out of the buffer that is provided and copies it into the actual image in Vulkan, right? And we'll see a little bit how this works once we actually implement this method. The transition layout is to take the various layouts or image formats and translate from the old layout to the new layout. And we can provide those layouts here. Okay? And what this allows us to do is basically optimize and convert from the loaded image format off of disk to an image format that our engine or the graphics API can understand and use. And so we're actually going to use this quite extensively, especially in the future when we start supporting different formats of images and so forth. Okay, so that is it for the header file, the Vulkan image header file. So now we need to go into the C file, and I'm going to go all the way to the bottom, and just before Vulkan image destroy is where I'm actually going to paste these two methods. And I'll step through them and explain them sort of in the same order as I did in the header file. So the copy from buffer creates a VK buffer image copy structure, right? And we just go ahead and zero that out, and we go ahead and just explicitly set these things to 0. And the only reason that I'm actually doing this is just to sort of show you guys what properties are available. And then we go ahead and set the what's known as the image sub-resource. And we basically say that this is a color image, right? And that we're not using MIP mapping. If we wanted to use MIP mapping, we would need to add some things here. That we're not using multiple layers of images. I touched on layers earlier in the series, so that's just 0, and the layer count is 1, okay? And then the only other thing that we need to set is the width and height of the image extent, which we pass in the actual image itself. It's actually part of this Vulkan image. And then our depth is going to be 1, because we're not actually using 3-dimensional images. In this case, we're only using 2-dimensional images. So if we ever have a 3D image, which actually we will eventually have that, we'll need something, some enhancements in here to support that. But for now, we are just going to use 2-dimensional images. Okay, and then all it is just this VK command copy buffer to image. And as you might have noticed, since this is a command, that means it needs a command buffer, which is why we take this in. So the idea here is that this function is actually designed to be used in the middle of a command or a series of commands that is fed to a command buffer. So it just sort of makes setting this process up a little bit easier for us, okay? And then if we go up here to transition layout, so basically we have to set up a image memory barrier. And I know I haven't gone into a lot of what the actual barriers are, but you could basically take it into mind that a memory barrier states that any command that used the allocated memory that is fed to this barrier beforehand uses the old version of that, and then any commands that come after this use the new version after whatever barrier this is for, after its associated commands have run, right? So it literally is a synchronization point to say we need to make sure that absolutely sure that the operations that are using this barrier are complete before we execute the next set of commands, okay? So in our memory barrier, we set the old layout and the new layout as passed in. We set the source and destination queue family index. So this is basically saying what graphics queue we're using. We're just using the, or which queue family we're using. We're using the graphics queue index here. Here is the image itself that is going to be transitioned. Again, the aspect mask, the base MIP level, level count, and all those things, right? And then here we define the source and destination stage, and these can change depending on what the old and new layout are. So basically what we're saying is if we don't care about what the old layout is, in other words, it's set to undefined, meaning take any layout whatsoever, and we want to also change that to transfer destination optimal, which means that we want to transition it to an optimal layout for the underlying implementation as defined by the driver. So if we meet this condition where we say we don't care about the old layout, but we do care to transfer it to the destination optimal layout, then we're going to go ahead and set the barrier source access mask to 0 and the destination access mask to transfer write bit, meaning that we need write permissions on that, okay? The source stage, basically we just say we don't care where we are in the pipeline. It doesn't matter to us, right? And so in this case, we're saying we don't care about that, and that we're saying the destination stage is the pipeline stage transfer bit, and this is used for copying, right? Otherwise, if the old layout is destination optimal and the new layout is for shader read-only, meaning instead of loading from a file, for example, we have already taken the data out of a file, loaded it into a buffer, and now we want to change that into a layout that's suitable for read-only shaders, then we need to go ahead and set up the access masks for source and destination as the transfer write and transfer read bit accordingly. Shader read bit accordingly, rather. So the stage would be the stage transfer bit, the fragment, or the destination stage would be the stage fragment shader bit. Right, if we needed to use this in a different pipeline stage, we could put the vertex shader bit in here if we wanted to, if that's where we were actually sampling this, but we're not doing that in this case. We're only using it in the fragment shader. So there are some assumptions that are made in here. If we need something to expand on those, then we can always come back and enhance this, but for now, we're just going to sort of make some assumptions, hard code some things, and I think that's totally fine. So for right now, these are the only types of two transfers that we're actually going to support. So if anything else, any other combination was passed, we are going to abort, right? Because we don't actually have any setup for the source and destination, as well as the source and destination access masks, right? And then finally, we call the VK command pipeline barrier. And then we go ahead and pass it the handle, the source stage, destination stage, and then all these other things are things like our dependency flags, our memory barrier count, any memory barriers, which in this case we don't have any, so we just pass 0 for all those things. And this is actually what performs that transition of layout, okay? All right, So that is pretty much it for that. That is one of the main pieces that we're going to need when we actually go to load up a file. So that is Vulkan image sorted. So the next thing that we need is we actually need a way to define sort of a texture resource, if you will. And we haven't talked about resources yet. And resources is actually going to be a pretty a long-winded thing that we're going to be updating over time, because proper resource management is pretty paramount, right? So for now, we're not going to implement a sort of proper system because we want to get things up and running and visualized, and then we can go back and actually input these things later. So for now, I just want to kind of cover how this works, and then we can go back and reorganize later. So what we're actually going to need is next to the renderer folder, so under source, we're going to need a new folder, and we're going to call this resources. And under that, we're going to create a new file, and we're going to call that resource types.h. And resource types.h is going to have a pragma once and include math types, which includes our defines, because we're going to need those things eventually. And we are going to type def a structure called texture. And texture is going to be a little bit of a sort of an interface, if you will. So a texture is going to hold some basic properties like an identifier, a unique identifier, the width, the height, the number of channels, whether or not it has transparency, something called a generation, which we're not going to get into yet, and then a void pointer to internal data. This internal data will wind up being the graphics API specific data that is used by this texture. So we can pass around this sort of texture object and not have to be concerned about what is actually happening with that texture as far as the graphics API is concerned. So this is a level of abstraction, if you will. And so everything Vulkan specific will wind up being stored at this location, and then anytime we pass a texture to any of the renderer commands or the renderer functions, all we have to pass is the texture. We don't have to worry about the internal data. Okay. So the next thing that we're going to need is in our renderer types INL file. We are actually going to need to add something to our renderer backend, right? So we actually need a way to tell the renderer that we want to create a texture. We're going to add a couple function pointers here to the bottom. And I'm actually going to space this down so that we don't have to scroll sideways, because I can't stand that, and that's terrible. So this takes in a bunch of properties, and we might wind up actually creating a structure with this creation info instead of doing it this way, but this keeps us from sort of having to create that structure and pass it in, at least for now. So this is sort of the limit on the number of parameters I would pass in on a function. This seems like a little bit much, but for now I'm okay with it. So we have a create texture, which takes the name of a texture. Whether or not it should be auto-released, this is something that we are going to be adding in the future in terms of how many references we have to a texture. So this just passes that. It's just a pass-through right now. It doesn't actually do anything. The width, the height, channel count of that, the actual pixel data itself, you'll note here that that is a U8 array. So that is going to store 8 bits per pixel. And we are going to use a specific texture format internally in our renderer that will always be the same, so that we don't have to switch on that stuff. So here is just our pixel array. Then we'll also indicate whether or not it has transparency, and then of course a structure, a pointer to the created texture. Destroy texture just takes a pointer to a texture and destroys it. Okay, so that is our interface for the renderer backend. And so what I'm going to do is go to the renderer front end now, and I'm going to add two functions there, which, as you may expect, have the same signature as the backend, right? So they look exactly the same. Let me just space these down. Okay, so they look exactly the same. I don't know why it did that. Okay, so they look exactly the same as the backend interface, and that is intentional. Okay, so we have our renderer create texture and our renderer destroy texture. And as you might expect, when we go into the renderer frontend.c, go all the way to the bottom, we are simply going to pass all that stuff through. So we're going to call our state pointer backend create texture, right? And that's just going to access our texture or our function pointer there. And destroy texture will do the same thing, okay? And that is it, at least from the front end, right? So it makes it very easy for us to create a texture as long as we have these things to provide it, right? We say, here's what the texture looks like, here's its data, create a texture and return it. Great. So that is the front end. And now you may be wondering about the back end, right? So the back end actually has a few methods of its own. So I'm actually going to go into the renderer backend h file, and I'm going to paste more functions here that look very similar to what we've already done, right? And you'll note here that the texture type is not found, so we actually just want to go ahead and include resource types.h to get rid of that. All right. And so before we actually fill these out, I want to go into the renderer backend.c and connect our function pointers here before we actually forget to do that and then wonder why it doesn't work later. So all this is we have two new functions to point to here. So we have create texture and destroy texture, and those point to Vulkan renderer create texture and Vulkan renderer destroy texture respectively. And then of course, since we've done that, we will go ahead and zero them out on the destroy as well. So now that's hooked up, those can be used. Let's go and define these guys. So if we go back to our Vulkan backend.c, and we're going to go all the way to the bottom below create buffers. And I'm actually not going to paste the whole function in here because this is actually kind of long. So I'm going to start by just creating an empty function here, right? Here is our renderer create texture. The first thing that we're going to do is we're going to copy over a few of our properties to the out texture pointer, right? So we'll copy over the width, the height, the channel count, and we'll set the generation to 0. Again, we'll come back to what the generation is once we actually stand up our full-blown texture system, but for now, just accept that as is. So before we can continue with this, there actually is one more structure that we need to set up, and that is going to be in Vulkan types.inl. So let's go ahead and go to the bottom of that and just type def that real quick. So this is going to be called Vulkan texture data, and this is the internal data that we're going to use that's Vulkan specific, right? It contains a Vulkan image and that sampler we talked about, okay? So if we go back here now, the first thing that we're going to do is our internal data creation. And I've got a to-do here for this because we really should be using an allocator for this, but for right now we're just going to k-allocate some memory, and we're going to do that the size of a Vulkan texture data and just assign it, and then we'll go ahead and cold cast that here so we actually have the type to work with, okay? And again, this is something ideally that a custom allocator would be doing so that we don't have to call malloc, but we don't have that hooked up yet, so this will have to suffice for now. All right, so the first thing that we need to do is actually determine the image size. When I'm talking the image size, I'm talking the amount of pixels times the amount of channels, which will give us sort of the length of the pixels array, right? So our image size is going to be our width times our height times our channel count, right? And what we're going to do here, at least for now, is we are going to assume 8 bits per channel. Now, we can put some logic in here to actually detect, based off of these things, what type of format we're going to use. but this is already sort of long enough, so I don't want to do that, sort of right off the bat. So we are going to assume a VK format of R8, G8, B8, A8. So that's RGBA, 8 bits per channel, right? And we're going to use the unorm version of that. So the next thing that we're going to do is we are going to create a Vulkan buffer. And this is going to be a buffer for us to be able to load the data that is contained in pixels into Vulkan memory, right? And so we set up a usage, which basically is saying this is a transfer buffer. Our memory property flags say that we should use host visible memory and host coherent memory. And then we have a Vulkan buffer here called staging. And we go ahead and we create that buffer, okay? So once we have that buffer created, we want to go ahead and load the data into it. So we just call Vulkan buffer load data. We pass the staging buffer to it. We say we load it from the beginning. We pass the image size as the size of the actual buffer itself. And then we don't have any flags, and then we pass the pixels as the data we want to load into the buffer, okay? Next, we will actually call Vulkan image create. Okay, and this is actually not defined yet because we actually have to include that at the top. So let's go ahead up here and include Vulkan image.h. Okay, and we have here again some assumptions that are being made, and this is just fine. We can always extend this later to be a little bit more dynamic, but our image type is assumed to be 2D at this point. If we ever do a 3D texture, we'll need something more robust. But we pass the width, the height, the format is the image format is passed through as is. The image tiling is just using the optimal tiling mode as determined by the driver. And then our usage flags are it's a transfer source, it's a transfer destination. It is an image that is sampleable, and it is used as a color attachment. Now this is fairly specific to texture creation. You may not always use it this way, but in this case, since we are creating a texture, it's okay to make that assumption. We also want to use device local memory, and then we want to create a view along with it. We don't want to have to do that separately. And then the image aspect is basically saying it's a color. Its attachment aspect is a color. And then we go ahead and pass a pointer to the image to be populated. Okay. All right, so now we have an image. We have a buffer that we've loaded the image data into, and now we need to actually take the data that is in this buffer and we need to load it into our image. So in order to do that, if you recall, the methods that we use for that actually require a command buffer. So that means that we will need to allocate and begin a single use buffer. So we're going to call that temp buffer. We're going to use the graphics command pool and the graphics queue. All right, we'll go ahead and stand that up. And then we'll go ahead and call our new transition layout, right? And this is what is going to take it from a undefined layout to a transfer destination optimal. So now that we have that layout transitioned and the layout of the data is such that it can be transitioned over, we go ahead and copy the image data from the buffer. Now that we have copied the data over to the buffer, we need to transition the layout again, this time from layout transfer destination optimal to a layout that is optimized for shader read-only access, right? And this is what we need to set up in order to make it readable by the shader, okay? Once we've done that, we can go ahead and end the single-use buffer, okay? And that is our image created and our data copied over to it. So at this point, it's actually usable by the shader. However, if you recall, there was that second portion where we actually want to use, or where we actually need a sampler to sample that image properly within the shader, right? So there are ways to do it without this, but in our case, we actually want to use a sampler. So what we're going to do here is we are going to create a sampler. So what we have here is a VK sampler create info, right? We've just zeroed that out. And then our mag and min filter, these are basically filters that are used that determine how the texture should interpolate across as you magnify it and sort of minimize it and move away. And we're going to use linear interpolation for both of those. Our address mode, U, V, and W, you'll see this U, V, W a lot when you're talking about texture coordinates. So typically, when you talk about UVs, you'll hear that whenever you're talking about UVs, you're talking about, or UVW if you're using 3 coordinates, you're talking about texture coordinates. So the address mode in this case is that image that I had brought up before, where you have these different modes, right? In our case, you can see here that we're actually using repeat, which is this first one. So in this case, we're using anisotropy, which is a different type of texture filtering. We're setting the max anisotropy to 16 times. Again, this is probably going to wind up being configurable, hence this here, because not every graphics card is going to support that. So if any of you guys run into an issue with that, let me know, and I can double back to this and enhance that to actually switch on that. So the border color is black, which the border color again is used for clamp to border. So here this is black. We have defined ours as black, right? We're not going to use unnormalized coordinates. In other words, we want normalized coordinates. The only other important one here is the mipmap mode, which is sampler mipmap mode linear, which basically generates mipmaps in a linear using linear interpolation. If we are using mipmaps, which we're actually not technically, so we don't actually have to worry about what we set here. So I just chose linear. So that is the sampler create info. So as you might have expected, we have a VK create sampler, which takes that information and then stores it in our stores the created sampler rather in our data that we defined up here. Okay. All right. So obviously, if that fails, it's going to bleat about it and return. And then the only other thing that we want to do is at the very bottom, we want to go ahead and copy over the has transparency, as well as the generation. We want to go ahead and increment that. And again, the generation is basically saying how many times this texture has been refreshed or loaded. So it starts off as 0, and then it'll be 1 in this case. And we can use that to determine some things later on. So note that that is going to be important later on. It's not important right now, but do note that that is coming. And that is pretty much all there is to creating a texture, right? It's kind of a lot. There's a lot of pieces, but that is how we do it. So the second piece of this is actually pretty simple. It's destroying. So all we do here is cold cast the internal data to just a Vulkan texture data pointer. We call Vulkan image destroy. We destroy the sampler. Make sure to zero out any memory. We free the Vulkan texture data from this, right, the internal data, and then we go ahead and zero out the whole texture structure, right? And that's all there is to it. So this is pretty straightforward, thankfully. Okay. So let's go ahead and build, just because I want to make sure that we're all good to go, and it looks like we missed some things here, so probably missed an include somewhere. Right. So the renderer front end is bleating that this is only visible here, and that's because we didn't for declare it, and we did not add our resource types.h. So if we actually examine this a little bit further, we'll actually determine also that the renderer backend does not have it either. And so the real fix to this will be going to renderer types INL and adding the include here, right? Because both of those files use that. And so by including it there, we should have it everywhere that we need it. And so now we've built. And I'll go ahead and run, just to make sure that everything is operating as we expect, and it is. So we can still move around. We don't see any difference, and that is because we haven't actually loaded any texture data, and that is okay. So this is actually where I'm going to split this video, because this video has gone on long enough, and I want to actually have a clean break from actually loading up the texture data. So next time, we'll go ahead and round this out by generating a sort of test texture that we're going to use. And we'll generate that texture in memory, and that'll sort of be our default texture that we use. And we'll generate that and then apply it, and then we'll also need to set up our shader code to take in the sampler information and be able to actually access that information, and then we'll need to modify our shaders as well. So as you can see, there's quite a lot more left to do in it, so that is where I'm going to break this. Thank you guys so much for watching. If you have any questions about this, feel free to hop on the Discord. There's a link in the chat below. You can also leave a comment in the comment section below, and I will answer that as soon as I possibly can. If you like this video, toss it a thumbs up. If you haven't already, consider subscribing. Click the little bell icon there to get notifications as to when videos in this or other series drops, and I will see you guys next time.